Hello Calc class. This video will be viewed after Wednesday's class. 11:30:16 already, November the 30th. Alright, today we're going to look at curve sketching. So we're going to come up with the graph of a function without using the graphing calculator. And we're going to use a number of skills. So we always want to look at the domain. Excuse me. We are going to have a blast from the past and look at intercepts, X and Y intercepts. I will look at symmetry. So also about a blast from the past. Asymptotes. We are going to then enter calculus land and look and see where it's increasing and decreasing, and looking at local max and min, and concavity, what sections have what concavity, and then points of inflection. Alright, so that'll keep us busy. I'll just teach one example tonight, and you will sharpen your skills by actually doing some tomorrow. Alright, so y equals x minus 1 over x squared is our function of interest. So starting with the domain, we can see right away that x cannot equal 0 because of the x squared in the bottom. So therefore, we have a domain restriction, and that will remain throughout the problem. So we can list the domain in a fancy way: negative infinity, comma 0, union 0, positive infinity. So that is a way to express x does not equal 0. Right, just for your interest. When it comes to intercepts, you'll recall, you've been well taught, to find the x-intercept, you let y equal 0 and solve for x. So in this case, we look at y equals x minus 1 over x squared. Multiply both sides by x squared. And we get 0 equals x minus 1. Solving, we get x equals 1. So that is where our graph crosses the x-axis. So I'll go ahead and indicate that on a graph. Right there at x equals 1. We know 1 point on our graph. Alright, x equals 1. Now we talk about symmetry. There are three kinds of symmetry. One is about the y-axis. If whatever is going on this side of the graph is also going on this side of the graph, we call it symmetrical across the y-axis. So I can fold it along this line and get an exact imprint. And that's called symmetry, y-axis symmetry. And then there was symmetry to the origin, and that is, if you recall, every point on the graph, say we had like an ellipse, which isn't a function, but it is an expression, a relationship. So if you draw 100,000 million billion lines through the origin, on each one, the values on the graph are equidistant from the origin. And that was called symmetry to the origin. And then there was symmetry to the x-axis, where whatever is happening above is also happening below. Alright, so this one, because we're dealing with functions, this will not pass the vertical line test. There are, let me find you one that has symmetry to the origin that is a function. Alright, there's one. So if I draw all these lines through the origin, you'll see they intersect with my graph equidistant from the origin. So I should have done an example that was a function. Let's stick with functions. We are in function land. So we're going to look for symmetry across the y-axis and the origin, but we're going to skip the x symmetry across the x-axis because they are not functions. All right, so the algebra for y symmetry is, if you recall, f of minus x is going to equal f of x. So we'll examine our function and see if it's symmetrical across the y-axis. And for the origin symmetry, the test will be if f of negative x is the same as negative f of x. All right, so, and you can look back to your old notes. Where are those comp books? And you can see we established that in pre-calc. All right, so let's do the test on our function. I'll call y f of x for this part. All right, so here's our function, and the test requires us to put in negative x. So what happens to our function when x is replaced with negative x? Well, this becomes negative x, and this becomes negative x. So simplifying, I get minus x minus 1 over a positive x squared. So I can observe the original. The y symmetry says when I do that, I come out with the original function. This is not the original function. So it does not have y symmetry. Does it have symmetry across the origin? It says it comes out identical except everything's negative. And here, for this to be the complete negative of that, this would have to be negative, which it is, but this would have to be positive, which it is not. So it doesn't have any symmetry. None. When it comes to symmetry, there is none. All right, so that kind of helps us with our sketch. All right, let's keep that under our hats and look at the next thing, which is asymptotes. And again, dipping down into the pre-calc era of your life. All right, so y equals x minus 1 over x squared. The vertical asymptotes are what causes the function to be undefined, and the denominator equals 0 at x equals 0. So that will be, so far we've got a intercept at 1, and an asymptote at the synonymous with the y-axis, which is x equals 0. And for the horizontal asymptotes, you'll recall we had 3 cases. And the case where the denominator is larger has the degree greater than the degree of the numerator. This is degree 2. This is degree 1. The horizontal asymptote is always y equals 0, which is the x-axis. So that's what we've gleaned so far. So we've done domain, intercepts, symmetry, and asymptotes. Now, welcome to the calculus. We're going to look at increasing, decreasing, which you'll recall is the first derivative. And we'll also do local max and min. They're closely related to increasing, decreasing intervals. So let's take our function, and I'm going to rewrite it like a product just because I prefer the product rule. Actually, the quotient rule will give you the exact same answer, and it isn't too difficult, but I just choose to do it this way. So the first derivative is the first, And you can work ahead of me or without looking. The first times the derivative of the second plus the second times the derivative of the first. All right, so let's clean it up. And I recommend spending a lot of time cleaning up your first derivatives when you have to do a second derivative. It always helps. So I'm going to write this a little more clearly. So I'm going to distribute the minus 2 to the x and the minus 1. And this x to the minus 3 I'll put in the downstairs position. And then this equals 1 over x squared. I prefer one term over 2, so I'll give it a like denominator. All part of the cleanup process. So when I do that, I'm going to get minus 2x plus 2 over x cubed plus x over x cubed. So putting that all together over x cubed, I get minus 2x plus 2 plus x. And that can simplify by combining like terms. A minus 2x and a positive x is a minus x and a positive 2. Upstairs, downstairs is the x cubed. All right, so do you see how cleaning up that first derivative is really going to help? All right, we're going to set that equal to 0 to find the critical points. We see that the first derivative does not exist when x equals 0 because it causes the denominator to zero out. So that's one place that's critical. And the other part is setting this equal to 0, which ends up just setting the numerator equal to 0. Always works that way. And we get x equals 2. All right, so we found two critical points. So we like to graph them in this number line fashion. So here, x equals 0, it did not exist, the first derivative, and x equals 2, we had a 0 first derivative. All right, so from here to do increasing, decreasing, we like to do test points. So I'm going to test -1. Where do I test it? I want to know whether the first derivative is positive or negative, so I do throw it into the first derivative. This is the best form for that. So I get a 2 minus a minus 1, which is positive, over a minus 1 cubed, which is negative. So a positive divided by a negative is a negative. All right, then in this interval between 0 and 2, I'll test 1. And that gives me a positive over a positive. And then over here I will test 3. Throwing it 3 into there, I get a negative over a positive, which is a negative. All right, so looking here, we see that this is decreasing between, so it's going to be decreasing between negative infinity and 0. Decreasing. Then it's going to be increasing. It's also going to be decreasing from 2 to infinity. All right, and then the increasing part is in between from 0 to 2. All right, I'll come back. I'll do right now. And so this also is a good place to stop and see where we have local max or min. And where the derivative does not exist, we're not going to have a local max or min. So there's a possibility here at x equals 2. And you see it's increasing on this side, zeroing out and decreasing on that side. So we have a local max at x equals 2. So max, local max at x equals 2. What's the y value? Go back to the very, very original up here, and we put in x equals 2. I get 2 minus 1 over 2 squared, which is 1/4. All right, So my timer went off, so we'll finish this on part 2. Alright, so my local max at 2 1/4.